Hello, so today we are going to do this problem, which is part of Leetcode weekly contest 332. The problem is the last problem, subsequences with minimum score. So we get two strings, S and T, and we are allowed to remove any number of characters from T, okay? And we have this concept of a score where it's 0 if no characters are removed from T, right? Otherwise, if we want to remove characters, then we have the left side and the right side of what we want to remove. And so left would be the minimum index. So the first letter we want to remove, right would be the last one. And the score is just right minus left plus 1. And the goal of the problem is to return the minimum possible score to make T subsequence of S by doing this removal here, okay? And subsequence is just a substring where you can skip characters, right? So you can delete some characters. So for example, A, C, E here is a substring, is a subsequence of this string, okay? Okay, so that's the idea. Now, for example, if we apply to this first one, we get, so we can remove Z, and then B, A, A is a subsequence because you have B, A, A, right? And so what did we needed to remove? What's the score? Well, we removed just index 1. So right is 1, left is 1. So 0 plus 1, that gives us 1. So that's roughly the idea. Now, both S and T can be up to 10 to the power of 5. So this immediately tells us that we can't do something that is O of the length of S by the length of T, right? So we need to think about something else. So let's see how we can solve it. Okay, so how do we do this? So the problem says we want to find the minimum possible score, right? How do we minimize the score? Well, what we want to remove, so we have this, let's suppose this is T, right? So we want to remove the minimum possible stuff in the middle so that the score is minimal, because the score is just, let's say this is the right, this is the left side, this is the first one we remove, this is the right we remove. The score is going to be R minus L plus 1. So to minimize the score, we just minimize this window here. So that's the first part. And what does minimizing this window means? It just means that we need this prefix here that we are not removing, and this suffix here to be large as possible. So we need the longest prefix to find the longest prefix and the longest suffix. The other part is that since the problem here is actually, well, we do not want to remove, so let's say here, this is, let's just make this a little bit bigger. Let's say this is L and this is R. So these are just the first we want to remove and the last we want to remove. There could be some elements here that we do not remove, right? But it's always better to remove them because we already are incurring the cost here, because there is one after it that we need to remove. So we are already incurring the cost. So may as well just remove it, right? Because if we remove it, we have a higher chance of finding that this is a subsequence. Because if we add a letter here, if we consider this letter here, let's say it's A, then that may take from another A that maybe is in the suffix, right? So that will simplify the problem where we don't need to worry about what's in the middle, whether we want to remove it or not. Let's just suppose we remove everything between L and right, and only think about getting the prefix, the longest prefix and the longest suffix that are a subsequence of S, right? Okay, so that's the first idea. So that's, let's say this is T. T is some sort of T0, T1, all the way Ti, all the way to T of the length of T minus 2, T of the length T minus 1. So we need to find some sort of prefix and suffix that are as large as possible, right? And then those are the ones that we need to find that they are a subsequence of S, because this part here is what we want to remove, okay? Okay, so what does this mean? So this just means finding the prefix on the left and the suffix on the right that are as close to each other as possible because we want to maximize them, right? So we want them to be as close to each other as possible because the closer they are, the smaller the part that we need to remove, the smaller the score. Okay? So that's the idea here. Now, how do we do that? Well, the first thing we need is we need to keep track of the leftmost index of S. That makes a prefix of T a subsequence, right? Let's define it more formally. So let's say that left of I is going to be the leftmost index of S, such that from S0 to S of left I, right, has T0 to Ti as a subsequence, right? So let's say we have, this is S, right? And this position here is left, it needs to be left of I, and this is T. So this is T of I. So the definition of left of I is just the leftmost index in S, such that the prefix on T is a subsequence of the prefix up to left of I, right? Okay, so let's just clarify that more concretely. So let's say we have S here and we have T, and this is some index X, right? Then the definition of this X here, let's say, is left of I that we are going to calculate. Then we just want the prefix of T up to I to be a subsequence of this prefix of S up to this value X, which is the value we store in left of I. Okay, so this is left of I is equal to X. That's what we want. So subsequence means maybe, let me give you an example. Let's say here we have maybe A, B, A, C, right? And this is maybe B, A. Or maybe here we have D and then here E, right? So why is this a subsequence? Because, well, we only want the leftmost, so let's maybe just say this is another, let's say this is E and this is A, right? So you can see here there is a match because we have B and we have A. And this is the leftmost. We can't be here because then we have a match here at A that is larger, right? So here, this position here, position of A, right, gives us that this prefix here, BA, is a subsequence of A, B, D, E, A, right? Is a subsequence. So what we'll do, so I'll say 0, 1, 2, 3, 4, and this is 0, 1. So what will happen is we'll say that left of 1, so that's the index in T, is equal to 4. And all what this says is basically that the prefix of T up to, at I, right, is a subsequence of the prefix of S at left of I, right, left I. That's the definition here. So once we have this, the idea of this basically is that it will give us the largest prefix. So this left of I will give us the largest prefix. And so if we do something similar for the right side, we'll also get the largest suffix. And since those are what we are looking for, right? The max prefix and the max suffix is what we are looking for, because then we can just subtract and get the score, right? And so let's apply it to a string here. Let's apply it to this string. So what we'll do is we have A, B, A, C, A, this string, and I have the indexes here. So first we initialize left to 7, just a value that is really big that won't get any matches. So that we want to take the leftmost, so we want to take the smallest left. So we pick a big value so that this one is always smaller. Okay, so S is this and T is this. So first we are here at this position here, and we are looking for a match. And so the first match we have is this B here, which is position 1. And so for position 0 of T, right, so these are the positions of T, because 0, 1, 2, 3, so this is T, positions of T. And so for position 0, the subsequence in S that this one, the prefix of S is that this one is a subsequence of S, subsequence of ends at this position here, which is position 1, and so we put position 1 here. Now we stop, because once we reach this z is not in the string, right? And so we will never find a match, and so all of these will be 7, because b's, once you have z here, you'll never find it in S as a subsequence, because Z is not in S. So even if you take this one here, BZA, still it won't be a subsequence because of this Z. So those will stay at 7, the largest value. Okay. And now for right, we'll initialize it first to -1, and we'll do a similar thing that we did here for the left side, except we'll do it on the right portion, right? So here we had B, and so we'll go on the right side, and we'll check, is there a match here between A and A? Yes. So that means this position here is to change to say, what's the index? And that index is 6. And so we move here, there is no match, and so we move the pointer here for A, and now there is a match, right? And so now there is a match, we need to record it, because A is a subsequence of this portion here, right? That's what that means basically, and so the match here is 4. And now if we move here, again, we stop, because Z, we won't find a match, and so we won't find a match here either. And so we stop here. Okay, so now we have the largest prefixes, positions. Now we need to find the best score, right? The value in between, right? This here. So how do we do that? Well, what we can do is just go through these left and right indices, right? And anytime we find, and basically just check if the position at right is smaller, the value is smaller than the position at this one, then that's a valid possible removal that we need to check the score for, right? Because if right is bigger, then that's not valid, right? Because if right is here and left is here, that's not valid, because there is nothing in between. So we want to consider only those where left of I or is smaller than right at the position J, right? And so what we are going to do is we are going to start our J from here and our I from here, and we'll check. Okay, so 6, this index here is 0, 1, 2, 3, and the indexes here are 0, 1, 2, 3, okay? So the index for right at 3, 6 is small, 1 is smaller than 6, right? The values, okay? And so how do we find the score? Well, the score is just R minus L, right? Plus 1, right? And so to do that, then the score here is going to be equal to J, and we keep track of the best. So the best, we can just initialize it to the length of T, because worst case, we just remove the entire string T, right? And so here it's just length of T, which is 4. So here it's 3 minus 1, right? Plus 1. So that's 2 plus 1. So that's so that's 3. Sorry, I made a mistake here. It's actually it's not plus 1 here, because it's minus 1, because we want what's in between. So we need to remove the R part. And so it's going to be J minus I. Score is going to be J minus I minus 1. And so the first one is going to be 3 minus 1 minus 1, minus 0 actually. 3 minus 0, and then minus 1 here. So that will give us 2. Minus 1, that will give us 2, and so we put 2 here. And so the best, since this is smaller, this becomes 2. Okay, so now we do it again. We move our J pointer. So our J pointer is here. This is 2. So 2 minus 0 minus 1, it's equal to 1. So our score is now 1, and the 1 is better than this one, so we have 1. You could also just traverse it normally with G here, except what we need to do, make sure we do, is we skip minus 1, because that means there is no suffix there, a valid one. So we need to skip the minus 1s. Okay, so now the best score is 1, and we return that, and that's pretty much it. So that's sort of the idea, is computing left and right that represent the max prefix and the max suffix. And from there, we can define the best score by just pairing them together, right? Pairing the max left with the max prefix with the max suffix. Yeah, and that's the gist of what we are going to implement. We will add a little bit more details, but this is the gist of the idea. Now let's implement it and make sure it passes test cases. Okay, so let's implement what we saw in the overview. So first we need just the length of both strings. So I'll just call them an S and an T each for each string. And we need to define the score. And we said the score at worst case, we can just remove the entire string T. So let's initialize it to that. So this would be actually the best score. Let's call it just best. And then we need a left for the left array, and we said we are going to initialize it to the length of S, because that's going to be bigger than any right value, and so we won't match that value with any right because it won't be valid. Okay, and so this is going to be for NT because this is the length of T. This is the prefix of T, right? And then for the right side, it's going to be initialized to -1. Right, so let's just move it here, and now let's calculate the for left. Now left, we need a pointer for T. Okay, let's call it I, and so for I in the range of NT, or actually let's call it G. So this is pointer for T. Okay, and so this is going to go through the string S. And we want to check if S of I is equal to a J, then we found a match, right? So we want to increment our J pointer, but we also want to assign for J, because remember this is for the prefix for T that matches the prefix for S, and so we are going to say this matches because we just found a match, so it matches at I, so we assign that, and then we increment this. Now, we just want to handle one special case, which is if J is equal to the length of the string T, that means the entire string is a subsequence of S, right? So that means we don't need to remove anything. We just need to return 0 because we don't need to remove anything, so the score is 0. The best score is 0. You can't beat 0 in the minimum score with the minimum score. If we find that its score of 0 is valid, then that's going to be the minimum. Now, one thing we want to do here is that we just found that up to J, this is a subsequence of S, right? And so maybe this is the best score. So we just remove the rest of T and just use the prefix of T, right? And so in that case, the score is going to be equal to just using this prefix. And so if we use this prefix, right? So basically, T up to J is a subsequence of S, right? So what this means is we can just remove T from J plus 1 to the end, right? And calculate the score of that, and that would be one possible score, right? And so that's exactly what we are going to do here. What's the score of this? What's the size of this? Well, this is just the length of T, right, minus J minus 1. That's what the size of this is going to be, right? And so that's exactly what we are going to do here. And this is what we are going to compare against the best. And so it's going to be the min of score and the best so far, right? So instead of actually doing this here, let's just put it here, okay? Okay, so that's for the prefix side. Now let's calculate for the suffix, or the right side. So for the suffix, we want to just go in the reverse from right to left. That's what we did in the overview, and so we are going to do from -1, from the NS -1 all the way to 0. That's what this will do. And we want to check again if we have a match similar to what we did here, right? Except our J value here, since we are matching from the right, needs to be assigned to the last index in T. So that's NT -1, the length of T -1. Okay, so if they are equal, then we know that we want to decrement the pointer for t because we just found a match. But the other thing we know we need to do is that we want to say that the right at j, right? Basically, this means that t up to j is a suffix of s. So we want to record that. So we want to say is a suffix of s up to I, from I, yeah, like this. And so we just want to express that and assign I here, okay? And similarly here, in the same way that this is a possible score, and so we need to compare it, in a similar way, this here also is a possible score, which is that that t from j, let me just make sure this clear, from j to the end is a subsequence of s from I. And this is, of course, just to be clear. And so what this would mean is that we can just remove the prefix. So we can remove t up to I, right? And so what is this? What's the length of that? Well, the length of that is just I, right? And so that's exactly what we are going to do here. So this is going to be I. Sorry, j, that's what I meant. This is going to be j. This is j, so the length of that is j. Because j is the index for t, I is the index for s. Okay, so that's the other part for the right. So we calculated, but at the same time, we calculate the score of just removing just a prefix or a suffix, right? Because here we find that it's a subsequence, so we can just remove the suffix. And this here we find that the suffix is a subsequence, so we just remove the prefix. Okay, so now once we have that, now we can calculate where we are taking the max prefix and the max suffix and removing just what's in between. And so to do that, we need a pointer that goes through t. And we need, so this is going to be, j is going to be the right side. And we will need a pointer for the left side, which is going to be I, okay? And so for I, we will initialize it with -1 first because we don't know yet. And so we're just going to check while this is smaller than j, because that's what we expect. If we are taking left and right, we want the left side to be smaller than the right side. Because we initialize it to -1, +1 here is going to start from 0. And so we also need to make sure what's in the left side is smaller than what's in the right side, basically for the interval to be valid. And so we are going to say left of I +1 needs to be smaller than the right, okay? If that's the case, then we want to increment our I pointer because we want to get the max possible prefix. So max, to get the max possible prefix, right? So we want to keep incrementing as long as it's valid so that we can get the max possible prefix. Now, if we are here and we find that A was actually updated, I was updated, so it's different than -1, this means there is a valid prefix, right? And there is a valid suffix, right? And so we just need to update the score, and the score is going to be the, basically, what we are going to do is we will use t up to I, this is the prefix, and we will use t from j, right? And so, and we are going to remove what's in between. So I +1 to j, right? To j -1. And with the size of that, right, that we want to remove, the left side is, that's going to be just j minus I -1. So this is what we want to remove, and this is the score for it. And so we need to min that with the best score. And so we'll get that as best, and then at the end we just return best. And that's pretty much it, right? So that's roughly it. The main idea here is calculating the left and the right side. This should be easy to understand, but if you don't, just run it on an example. And that's pretty much it. Now let's run it. Make sure it passes test cases. Looks good. Let's submit. And it passes our test cases. Now, in terms of time complexity, this here is going to be of the length of s. So let's call it O of ns. This loop. This other loop is O of s. This loop is O of t. And so you can see overall, even though we have this here, the maximum things we can go through is the length of t, because of this I that goes through just the length of t. And so overall, this is going to be O of ns plus, because ns plus ns plus nt is going to be O of 2ns plus nt, so it's just O of ns plus nt. These are the length of s and the length of t time. Now what about in terms of space? In terms of space, we are using this left list and this right array and left array, and each of them is of length nt. So overall, we are using O of nt space. And this should pass fine because it's going to be to magnitude of 10 to the power of 5 for the time, and similarly for the space. So it should largely pass. Yeah, so that's pretty much it for this problem, what I wanted to cover. Please like and subscribe, and see you on the next one. Bye.